Hello, everyone. We're going to start on section 9.2 relating pressure, volume, amount, and temperature, the ideal gas law. We're actually going to divide this section into a couple of videos because there's actually quite a lot going on here. So in this first video, we will discuss the first learning objective, identify the mathematical relationships between the various properties of gases. This will eventually lead to something called the ideal gas law, but we will not quite get to that in this first video. During the 17th and 18th centuries, there was a lot of work done on trying to understand gas properties for the purposes of making things like hot air balloons work. So that's kind of when a lot of this work was done. So it was done quite a long time ago, and is even, we would say, one of the first things that chemists were able to do, or scientists, I should say. I don't know if they were identifying yet at that time as chemists, but in terms of the things we cover in a chemistry course, this was one of the first scientific things that was done. So there were several what I would call simple gas laws that were developed during this time, where scientists would look at two properties together. And this is a good scientific way of doing things, where you vary one thing and see how that changes another thing. So you're changing one thing, looking at one other thing, and holding everything else constant. So that's how they initially approached this. And from that work, we ended up with a lot of simple gas laws, where we're looking at the relationship between two specific properties of the gas, where everything else is being held constant. So we'll look at those gas laws. One thing I want to talk about as we get to this first one, pressure and temperature. As we go through these, each one of them has a name associated with it. So this one is called, this is actually the first time I've seen this name, Amonton's law. And the reality is that some of these are attributed to different people depending on the source you use. So this source is giving me a bit of information. All of that to say that I don't care that you remember the names of these people. That's not what we're studying here. We're studying what they came up with. So you'll hear this one, you'll hear Charles' law, you'll hear Boyle's law, lots of different names of people. You don't have to remember those people. You don't have to remember their names or which name is associated with which of the different laws. What I care that you remember is the relationship. So the first relationship is between pressure and temperature. And we're showing a schematic here of that relationship. So if we take a gas and we heat it, so we're starting off with this gas, and again, everything else is held constant. So what that means is that the gas has to be contained, right? We're not just heating the air because the air can kind of flow around, go somewhere else in the room. If we do that, we're heating a gas that is contained. So what we can see as we do that is if we heat the gas, we will see the pressure go up in the gas. This is the relationship. As the temperature increases, the pressure will also increase. And this is even some of these are things you could even try out potentially at home with some balloons. So changing temperature of the balloons, do they shrink or get larger? That's actually not quite this one, but that's getting at a similar idea. We'll actually talk about that law a bit later. But the idea here is as you increase the temperature, the pressure will also increase. And this is showing, and we'll be doing actually some labs where we will be collecting data similar to this. This is showing that relationship. So as you increase, so you're probably starting around here somewhere. As you increase the temperature, because actually you're probably starting right around here. As you increase the pressure, you're increasing the temperature. And then maybe you can cool it down a little bit and see that that trend continues to hold. And what you'll notice here is that there's kind of a dotted line here. This dotted line is indicating, well, we don't maybe actually have data for the gas in this region. Part of that is because gases eventually become liquids if you cool them down long enough. So we don't always have that data, but we call this extrapolate. If you extrapolate backwards, what you'll end up with is this intercept. So when the pressure goes to exactly zero, according to this data, we call that interception absolute zero. So we talked earlier about the different measures of temperature. We have Celsius, we have Kelvin, and we talked a little bit about, 0 Kelvin is absolute zero. That's what this is talking about. That is, experimentally, we can show that this line, goes back and intercepts at zero. So that's where that idea comes from of absolute zero. There have been experiments done trying to get very, very close to absolute zero. And there was even a Nobel Prize won for the people who were able to get the closest to it. So that's an area of continued research. But the idea is when you're at absolute zero, that is kind of, you don't go less than that. And there's additional reasonings for that we won't get into until next semester. But right now, scientifically, we can do experiments that show that there is a point here, and we can actually test that out in the lab and get something that's in the right ballpark anyways. Okay, so that's the idea of absolute zero. So what we're showing here is this linear relationship. As one goes up, the other one goes up. And we can show that in a few ways. This first way is we're saying it's a direct proportion. So pressure, this symbol means directly proportional. Pressure is directly proportional to temperature. And so again, that means as one goes up, the other goes up. Another way to write that mathematically is to say pressure is equal to a constant times the temperature. So we're writing that here, pressure, and so the K here is the constant. Pressure is equal to a constant times the temperature. Okay, so that is the simple gas law that this data is showing us. As one goes up, the other goes up. How we often set this up, however, is a little bit different because this constant is somewhat dependent on the context. So it's not a constant like Avogadro's number or say a molar mass where you can always go and look it up. It depends on the context. So we don't really care about this constant too much. What we often do instead is we talk about this ratio. So we can do some algebra and write it in this way. So pressure, so taking this and basically dividing by the temperature, pressure over temperature is equal to a constant. And for that specific system, that will always be true. So how we often use these types of equations is by looking at the change as we go from one condition to another condition. So we might say condition 1 and condition 2. This is very similar to our dilution equation where we had an initial concentration and a final concentration. So we say 1 and 2. So pressure 1, temperature 1, pressure 2, temperature 2. Both of those are equal to whatever this kind of random constant is. So pressure 1 over temperature 1 equals that constant. Pressure 2 over temperature 2 equals that constant as well. Again, because that constant is kind of random, what we end up doing is we end up using this equation right here. Pressure 1 over temperature 1 equals pressure 2 over temperature 2. Okay, so this is basically the form of this gas law that we want to use. A ratio showing the relationship between pressure and temperature and how we would use that to find one of those missing variables. So if we know 3 of those 4, we can find the other one. So one other thing to be aware of as you're using this is that when we are using temperatures here, they have to be on the absolute scale. So absolute scale is the Kelvin temperature scale. So we can't do this in Celsius. It always has to be Kelvin. Always has to be Kelvin when we use any of these gas laws. And that is because when we look at ratios, we do have to have an absolute scale for that in order for that to work. For example, let's say you had 1 degree Celsius and 2 degrees Celsius. It's not twice as hot when it goes from 1 degree to 2 degrees. It's actually still fairly cold, at least in terms of how we would interpret that. So just be aware of that, that you have to have these in Kelvin when you do these calculations. Okay, so there is an example here, so please take a minute to look at that when you get a chance. The other thing to mention here is you do need to have all of the same units. So we talked about pressure units in the previous section. If they're all atmospheres, that's fine. If they're all torrs, that's fine. If they're all kilopascals, that's fine. But if they're different, if pressure 1 and pressure 2 are not the same, you would have to make sure that they are the same. The other thing you might want to be aware of as you're looking at this, this question is you want to ask yourself, what would you expect the answer to be? In terms of, do you think the number is going to go up, or do you think the number is going to go down? And so you're basically going back to the definition of that simple gas law to answer that question. So partly you want to be able to do the calculation, but then you also want to be able to check your work to see if you've done it correctly. So do they go up together? Do, that's what you would expect. Do they go down together? You would also expect that. But if pressure is going up and temperature is going down, then you've done something wrong. So just that's something to be aware of. You need to be able to both do the calculation and correctly predict the direction of any change you would see there. So please take a look at this example. I would actually recommend that you pause, go through this example before we move on to the next one. So I'm going to go ahead and talk about the next one. I'm going to go through all these simple gas laws in one video. They are all very similar. So we probably talked about the first one more than we will about any of the others. So this one is volume and temperature. And there's a similar relationship here to what we described earlier. So as the temperature increases, the volume will also increase. And similar to the previous set of data, we can extrapolate back. Okay, so if we go all the way down to 0 volume, what would that temperature be? That's where we would say we have absolute 0. So we could do a similar thing here to what we discussed on the previous gas law. And in fact, this is what I was actually alluding to there, where you could try this out at home with a balloon, blow up a balloon, put it in the freezer, and see how it changes. And if it shrinks or does it get bigger when you put it in the freezer? And then if you want, you could try it out in some hot water. Be careful with that because it might burst. So don't do too much of this at home, but you can maybe put it in the freezer and see what happens, and if it's consistent with what we're seeing here. So because of that, we're going to have almost the exact same relationship as we did for the temperature-pressure relationship, which is we have this direct relationship. Volume is directly proportional to temperature. So as volume goes up, temperature goes up. Usually it's the other way around. As temperature goes up, volume goes up. And so we can write that in this way, similar to what we did before. So volume 1 over temperature 1 is equal to volume 2 over temperature 2. So the derivation of that is the same as the derivation we had before. So I'm not going to go through that again, just the same idea. If they go up together, which is the direct relationship, we have this kind of mathematical relationship. Again, another example, again, I would recommend you pause the video, try to solve this before we move on to the next of the simple gas laws. Okay, so this one is going to actually be different than the ones we've looked at so far, and we will be doing some of this in the lab, and we'll be doing some of the others in the lab as well. So this is volume and pressure. So here we see something different. As you change the volume, let's say we'll decrease the volume, you'll be doing something almost identical to this in the lab, where you have a syringe and you can depress it or pull it out. As you depress it, what you would see is the volume goes down, the pressure would go up, and then if you pull it out, you would notice that the pressure would go down. you'll end up with data similar to what's being shown here. So you have some high pressure at a low volume, high volume at a low pressure, and you follow this trend between those. Okay, and the lab will be developing some of these kind of graphs similar to this. But in terms of the mathematical relationship, you end up with something like this. Pressure is inversely related to volume. So we're showing the same symbol here for that relationship, but instead of having another variable here, we have the inverse of that variable. So 1 over V, pressure inversely proportional to 1 over the volume. So then we could go through that same kind of derivation. So pressure is equal to a constant times 1 over the volume. If we rearrange that, we would get pressure times volume, so multiplying both sides by volume, equals that constant. So again, then you would take two of those, so one condition, another condition, set them equal to each other, and you end up with this formulation, which is what we'll be using. I'm just going to highlight the whole thing, but it's this last part that you'll be using. So the difference here is pressure 1 times volume 1 equals pressure 2 times volume 2. And that's how you get the inverse relationship. This one, so I mentioned the dilution equation earlier. This one, you'll notice, is more similar to that dilution equation than the other gas laws we've looked at so far. So you want to be comfortable using this one, know when this one applies, so pressure and volume. One goes up, the other goes down. So that's what that's telling us, and then also be able to use it mathematically. In terms of these graphs, we'll actually be going through something related to that in the lab, so I don't want to talk about that too much right now. Another example, again, I'd recommend going through this example at some point as well. This one is important in breathing. So you can look at that example and see kind of why that works the way it does. So when we breathe, why do we breathe the way we do? It's because of this pressure-volume relationship. It's called Boyle's Law. It talks about it being called Boyle's Law here, but again, you don't have to remember these names. Okay, the last one is moles of a gas and volume. So we haven't talked about moles yet. Moles is the other property of a gas that we need to be aware of. So this one, again, you can try this one out at home. If you take a balloon and you blow into the balloon, you'll notice it gets bigger, right? We all know that that's going to happen. So what you're doing is you're increasing the number of moles of gas in the balloon. As you do so, the volume increases. So this is, again, a direct relationship. As volume increases, moles increase. Usually we would say as moles increase, volume increases. And so we end up with this familiar form that we've seen before, where we have a direct relationship between volume and moles. So this is similar to the first two. So you don't need to do anything new here. Just remember how you did the first couple of ones, and the same thing applies here. As one goes up, the other goes up, and then also be able to do the mathematical calculations there. There is a very interesting simulation here where you can change these and see how they change together. And this is something we actually did during our online pandemic labs. So you can try that out as something to simulate if you're having trouble visualizing this, how that all works. That is it for this first video for section 9.2. We have a bit more to go, so there'll be another video for that, where we'll talk about the ideal gas law and how taking all of these other simple gas laws together, we end up with something that will describe any gas that you'll encounter in your life.